Welcome all. Thank you for joining today's AWRI webinar. My name is Jeff Cowie and I'm a Senior Enologist at the AWRI. In the spirit of reconciliation, the AWRI acknowledges the traditional custodians of the country throughout Australia and their connections to the land, the sea and the community. We pay our respect to the elders, both past and present, and extend that respect to all Aboriginal and Torres Strait Islanders peoples today. In this session today, we're going to take you on a deep dive to all things filtration, filterability, and some fun facts. But before we make a start, a couple of quick reminders. Anyone that's new to the AWRI webinars, if you would like to provide a comment or ask a question, please click on the Q&A button on the Zoom toolbar. You can do this anytime throughout the session, but we'll answer them at the end of the presentation. A reminder that this session's also being recorded. So yeah, if you want to revisit anything you saw, you can view that on the AWRI YouTube channel, and that will be either later today or tomorrow. So for anyone that's just joined, welcome. Today's webinar topic is filtration, filterability, and some facts. It's a great pleasure to welcome Dr. Paul Bowyer from Blue Water Filtration. Paul has initially taught wine chemistry and sensory analysis at Charles Sturt University in 1999. There for a few years, then moved to the University of Adelaide in 2003. He then joined the Lefort Australia Group in 2006 as their Australasian Technical Manager. In 2011, he's joined Blue Water Filtration as the group enologist and has been there for around 10 years now. During this time, Paul's been very active in promotion of wine filtration, filterability analysis, and also education in that space as well, to both Australia and also the New Zealand wine industries. So welcome, Paul. If you're ready to make a start, I'll hand over sharing permissions to you.
Yeah, great. Thanks, Jeff. All right, bear with me for a second. I'll get this show on the road. All right, can we see that okay?
Yep, all good.
Okay, good to go. All right, well, thank you very much, Jeff, for the invitation to present. This presentation is a contraction of something that's quite large. So there's a lot of information in here, and I would encourage anybody that wants to review it to go to the YouTube file that will be uploaded later and have a look through it. If there are any further questions, please don't hesitate to flick me an email on the address you can see there, or just go to the company page and you can find my phone number easily enough. So just a bit of an overview. Wine filter types, many and varied, everything from something as simple as a stainless steel screen, which most packaging facilities use, all the way down to membranes at the pointy end of the spectrum, and everything in between. And I think people will be familiar with at least some of those filtration options, but broadly they fall into two categories. Either a barrier filter, which is what membranes are, that are not meant to take a lot of load but provide a defined porosity, or a depth filter, which is meant to take load and has usually a much broader matrix. And you can see two examples below there of a pleated membrane, and on the right hand side you can see a depth filter, which is much more like a network sponge, which is meant to take a lot of load. Typically a depth filter like the one on the right is about 80% air, or void space, and that's there to accept load effectively. In terms of wine filtration, the most common forms that you tend to see around the place are things like pads, which are inexpensive and used to contain asbestos, but for some reason don't anymore. Typically they're either cellulose and DE mixed together or just cellulose. They're very flexible, lots of grades, bit of a pain to set up, and sometimes to dispose of if they have diatomaceous earth in them, but they're quite a versatile thing. Lenticulars are the same sorts of things as sheets. They have the same material in them. They're just in a condensed format that's easier to handle and goes inside a sealed housing, so you don't have any issues with drip loss or O2 pickup. There's lots of different examples on the market, but they do vary in quality, and You can see, for example, something like the one on the left that has a nice, strong stainless steel core is going to be quite resilient to stress. And this is one in a bin that you can see on the right-hand side that's still intact. And the large one on the right-hand side that looks all over the place has a weak core. So that's one thing that's worthwhile looking out for in those, good construction, in other words. In terms of Crossflow, that's a relatively modern way of filtering wine, and it's a little bit unique in that it uses a relatively tight filter, which is typically a 0.2 micron membrane, in one pass. Now, if you tried that with a cartridge filter, it would block pretty much instantly, but Crossflow has a unique design that allows it to continually clean the surface or sweep it free, concentrate all the retentate material, and basically give you clean permeate wine at the end of the day. But they're not a replacement for other types of filters necessarily. Very useful cellar tool. They don't produce sterile wine because the membranes are nominal and also are not integrity tested typically as part of the process, and that's what you require to have a sterile wine filter in play. They can also cause some very odd colloidal effects on wines, and for that reason I don't think they're a good thing necessarily to be using immediately prior to packaging. I mean, you have to be careful about the time window, which I'll talk a little bit more about towards the end. But as I said, Crossflow is a different type of filtration to the other types that I mentioned before. So whereas Crossflow uses the wine flux to sweep the surface of the membrane clean and applies pressure to push that wine across the membrane to give you a clean filtrate, dead-end filters like cartridges and sheets and lenticulars and so on just push straight through and so block, and eventually flow is restricted. So two very different types of filtration there. Onto membranes, which is where all the research tends to be done and the modern developments lie. They come in different formats, but essentially they're all tested against microorganisms, and that's one thing that you should look for in any membrane that you're using is the retention capability. The log reduction value is usually how it's classified, so always check that. In the relatively recent past, mostly you saw nylon membranes in use, but these days they're very much more polyether sulfone for various reasons that I'll explain briefly in a moment. Usually you find just under 1 metre squared per 10-inch segment, so that means the pleating is fairly tight. But if you go too tight in the pleating of a filter and try and pack too much area in there, then you can actually restrict the flow. Typically the most common format you see is called Code 7 30-inch. And what that means is it's a 30-inch filter, 3 10-inch segments that are thermally welded together. Code 7 refers to the end cap. So spear on top, double O-ring on the bottom with 2 locking lugs. In terms of the membranes, now nylon membranes have a uniform density. So if you picture looking at the end of the edge of something that's as thick as a piece of paper, which is what you have in a wine membrane, from one side to the other, nylons have a uniform density, whereas polyether sulfone is typically asymmetric. There's a tight central region that provides the microbial retention capacity, and coarser outer sections, inlet and outlet sides, which allow a much higher flow rate. And in terms of the plastics that they're made from, nylon is really good at hydrogen bonding just through the nature of the plastic itself. It has an amide linkage that's very good at abstracting anthocyanins from wine, and you can see that in the testis that's coloured significantly on the left there. On the right, polyether sulfone, the plastic is much more, the molecular structure is much more inert, doesn't hydrogen bond, and so usually the colour retention is next to nothing. In terms of how these packaging facilities are normally set up with filtration, probably the most common setup that you see is a lenticular housing followed by a 0.65 micron membrane followed by a 0.45. Something like that anyway, but that's the most common one that you tend to see around. And there is some thought that you could potentially swap out the lenticular phase with a Crossflow filter, which is feasible, but there are some caveats to do with filterability effects and colloids and so on that, as I said, I'll talk about a bit later on. Just to give you an idea of what this looks like in practice, on the left of this image, you can see the housings. So that's the filtration train. And on the right, you can see the filler, and the wine is basically pumped through the filters and then overhead into the filler. The most modern version of this is an automated system, and you can see a couple of photos of a system that's in a Torresen estate in McLaren Vale. The whole thing is much more tightly constructed due to, in this case, to the space available. But there are two trains, whites and reds, basically, lots of options for filtration built into that. And the whole thing can be run from a smartphone in terms of actual production or sanitisation or integrity testing. All of that can be done remotely, which is really the way of the future for these sorts of things. So you will see more and more of these as you go around. Just to give you an idea of how important it can be to monitor pressures across filters when you're actually doing a packaging run, and over time to make sure you get the maximum life out of filters and to head off any problems, I'm just going to show you a couple of slides. So in this one, you can see 4 filters in place. So the green trace across the top is the flow rate coming out of the filter train to the filler. The yellow is the first filter, which is a 1 micron large cartridge. The red is lenticular, which is next in series. Then the blue is 0.65 membrane, and the black is a 0.45 membrane. And these are the plots of the pressures across those filters over the course of around about a month. The yellow one you can see blocked early in that month. There was something that came through the line. In this case, I think it was diatomaceous earth that blocked up that filter. Consequently, flow rate dropped, which is the green at the top. So that yellow 1 micron stage 1 filter was changed out, and the pressure drops when the new filter's put in, of course. But you can see then that the next filter in line, which is the lenticular, gradually increased in pressure across that filter over the course of a month, right up until you get to around 250 kPa, so 2.5 bar, which is the change out pressure for that filter. But importantly, there's no load going on to the 0.65 membranes, which is there to protect the 0.45s, which equally has no load. So that's very much what you want to see when you're actually doing a filtration run, and in this case, it's over the course of a month. The next slide is over the course of 2 months, and it can show you what can happen if there's a problem and if you don't spot that. So in this case, 2-month span, the first month was a brand of lenticular that did its job. Similar to the last slide that you saw, the lenticular was taking the load, in this case, over the course of the month, up to the change out pressure of 2.5 bar. No load onto the 0.65s, the 4.5s, or the 1 micron filter, the yellow one up front. And as you can see across the top, the green trace flow did decline as the pressure on that lenticular filter increased up to the point of change out. When it was changed out to a different brand. And in this case, if you look at what happened on the red trace over the course of the next month, there was no increase in pressure. And that is very strongly indicative of a problem, because you always want the cheapest filter to be doing the most work, not anything subsequent, which in this case is the membrane. So the fact that the lenticular wasn't doing its job properly meant that the load was transferred to the next filter in sequence, which here is the 0.65, the light blue trace. And you can see the pressure across that elevated across the next month or so and forced a change out. And the cost of doing that is significant. In this case, you're talking about a 30 round or 28 round housing, I think it was. So not spotting that problem was a significant cost to that facility, put it that way. So that's explains to you why it's worthwhile keeping an eye on differential pressures across filters. Now, NTU and filterability index, typically for filtration jobs, NTU is still used as the primary measure of the condition of a wine, that the loading of particulate within that wine, what grade of filter should be used, and if it's going to be sterile filtered, you need it to be pretty clean or it'll block the filters straight away. So generally, everybody says, well, if it's less than 1 NTU, it's fine to go. That can be true in terms of the particle within the wine, but it doesn't really give you any indication of the non-particulate components within that wine that are not shown up through the measurement of NTU. That can take the form of something like a glucan, like we saw a lot of in 2011, for example, manoproteins, tannins, gum arabic, and other additives like CMC as well. All of these colloidal materials can cause significant problems to a wine's filterability, but you can't see it through an NTU measurement. And a lot of people think that there's correlation between NTU and filterability index, in that if you measure NTU, you can have a bit of an idea of how well that wine will filter. But it's definitely not the case. There is no correlation between these two. They are completely independent measures. So this is courtesy of Vinpac, 705 samples in this case. All of these wines are passes for filterability. They all have a filterability index of less than 20 seconds, which is what we say is a nominal value to work towards. They're all passes. So you have everything within that window. For example, top left-hand corner, you have a wine that has an index that's close to 0, which means it's perfectly filterable, but the NTU is 1.5. So there's a minor amount of material in that wine that is highly reflective. So you see a lot of reflectance and a higher NTU value, but it's perfectly filterable. On the other hand, we have a wine in the bottom right-hand corner that is borderline filterable in terms of the filterability index cutoff of 20 seconds, and yet it's less than 0.2 NTU. So visibly, it's extremely clean, but there's something in there that is actually causing some issues for the membrane. Now, there are a few different ways of measuring filterability index. Essentially, all of them involve pushing wine through a membrane test disc under 2 bar of pressure. The one that you most commonly see in New Zealand is the Rankine method. So basically, you push the wine through the test disc, you collect wine at certain fractions of time, and from that you generate a fraction, which is a filterability index. Typically in New Zealand, you see a cellulose nitrate test disc being used, but cellulose nitrate is dangerous goods, so it's not easy to move around the place, and it's not used in wine filtration anyway. And an important point about this is that it's a relative measure. Filterability is relative to the test disc that you're using and the filters that you're using in the packaging facility, so they should be the same. In this case, it's an issue. The method is a bit of a problem because there's human error involved. It's not an easy analysis to run. You have to swap beakers and so on to catch the relative fractions. And also you get small numbers, which make it difficult to draw the line as to what's a pass and what's a fail. Typically in New Zealand, 1.19 and below is a pass, 1.20 and above is a fail. It's a very narrow line. And I've seen, for example, an automated machine, which I'll show you a picture of in a second, that it ran the same wine 3 times in sequence, and the numbers that it spat out were 1.14, 1.17 and 1.24. So which one do you believe? And 2 of them are passes and 1 of them's a fail. So it's a problem. And the other thing is, because it measures volume for a set time, you can actually run out of sample. If the wine is clean enough, it'll actually run through that test disc, and you don't get an analysis result because it's sort of too clean in a way. So you can see there on the left, that's a couple of beakers, one for catching fractions and one for not. On the right-hand side is an automated machine that was constructed in-house to try and eliminate the human factor. The measurement that we advocate is the European method, which measures time for a set volume. So first of all, you can never run out of sample, regardless of how clean the wine is, because the volume is set 200 mils, 400 mils, and also a 600 mil time point as well. So it seems to be quite robust, plus or minus, say 2 seconds or something like that. You can never run out of wine. But always with filterability measurements, you have to look at it in conjunction with other data, like how big the wine volume is, the condition of the filters, how many filters are in the housing, temperature. All of these sorts of things play a role. So it's not just the be all and end all, but it forms part of the puzzle. If you want to know what it looks like, this is the most modern version of the filterability unit that we use. So all stainless, small footprint, etc., runs off a laptop. And what it spits out is something like this. Bottom right-hand corner, you can see there's a filter index and a modified filter index calculated. And also there are 2 charts. One of them is time over volume, or mass, which is inverse flux basically, and the bottom is inverse flux over time, which is something more like a blockage meter. So to give you an example of what you're going to see, this is mains water in McLaren Vale, which looks to be pretty ordinary with indexes of 9 and 12. RO water is much cleaner, 2 and 3 basically, but importantly, there's no blockage meter, and the flux chart is pretty linear. And a dodgy red wine is going to give you curvature in the flux chart and significant elevation in the blockage meter there, and an primary index of 69, and it didn't even measure the second one because it blocked the disc. Just to explain those two terms, filter index and modified filter index, the standard index is time to pass 400 mils through minus double the time to pass 200. So if you have 20 seconds for 200 mils and then 40 seconds for 400 mils, the index is going to be 0, perfectly filterable, no change in flux. The modified goes out to a 600 gram or 600 mil time point and covers a broader range and gives you a slightly different reflection of what you're seeing in terms of membrane effects, caking, colloidal impacts, those sorts of things. It's very easy to do. So to give you an example of what you might see between standard and modified indexes, in this case, the standard index is 21, which is pretty much a pass or just on the borderline, but the modified is actually 46. And you can see the curvature in the latter part of that test between 400 and 600 grams or mils in this case, which indicates that the membrane is starting to load up and the flux is slowing down. So this wine, although it looks to be close to a pass, if you just look at standard filter index, the modified tells you it could actually be a problem. So in general, a comparison between those two values is really quite useful. And generally, if the standard filter index is much lower than the modified, there could be a problem. But if it's the other way around and the standard index is much greater than the modified, which is typical, and certainly less than 20 seconds, then you generally don't see any problems. And this is the point. The filterability analysis is just taking the wine for packaging and putting it directly onto a membrane. So it's not referencing the pre-filters that might be in place, but that's fine. It's not meant to do that. It's very complex to do that. But what it means is if you get a pass by doing that, then you can be 99% certain there's going to be no issues at packaging because it's passed without the pre-filters in place. If you get a fail, it means you may have a problem, not that you necessarily will. That's when all the other factors come into play, like the temperature and the volume and the condition of filters and so on. At the bottom there is the point, ensure the correct membrane test disc is used. This is a really important point. It should be exactly the same as the membrane that the wine is going through on the packaging line. And to illustrate why that's so, this is one wine that was measured 4 different test discs, and you can see those flux curves are all completely different. Tell you what they are is PES cellulose acetate. And cellulose acetate is what you commonly find in laboratories for micro testing and so on. A 0.65 nylon in green and a 0.45 nylon in the purple colour there. And if you look at the indexes that you calculate from those, they're vastly different. So using a PES test this, you get basically a pass, very close to it. And that's a common wine filter membrane medium, of course. The nylon ones are much more elevated, so it's really important to make sure the test is appropriate and reflective of the filters being used at packaging. Now, Vinpack, just to give you an idea, they run a hell of a lot of analyses, and roughly, if you break it down, about 80%, so 4 wines out of 5 pass. About 1 in 5 failed, and there's a bit of a grey zone in between when you look at other factors to determine what needs to be done, if anything. And for the winemakers out there watching, just some practical outcomes here of wine additives, things to be aware of. It's common to want to try and touch up a wine on its way out the door to packaging through a concentrate addition or tannin or whatever it might be, just to show you some of the things that can happen with tannin. For example, 2011 Cabernet, awful wet vintage over here where this wine was from. So a little bit of colour was added to it. NTU was less than 1. The standard filtering gets 15 and the modified of 9. Adding that colour jumped the NTU up a lot and obviously caused an instant filterability blocked, and the disc locked in this case at 70 mils, didn't get anywhere near 600 mils. So then it had to be put back through Crossflow again, which basically took out most of what was added and cleaned the wine up. So if you want to look in terms of filterability charts, that's the base wine. That's when the colour was added, and that's when it was all taken out again by the Crossflow. So a bit of a pointless exercise in that case. Concentrate is essentially colloidal grape juice, so you've got to be quite careful with that one. In this case, base wine, 2014 Riesling, indexes of 8 and 24. So 8 is fine, 24 is getting up there, and the fact that the modified is 3 times the value of the base index tells you that there's something going on in this wine. But this wine was required for marketing, so it had to be filtered regardless of these numbers. When the concentrate was added, 5 grams per litre, Standard index went up to 50, modified over 200. So it had a very bad influence on the filterability of that wine. But as I said, it had to be run anyway, which it was. But importantly, it was sampled after the lenticular phase, but before the 0.65 membrane pre-filters. And what was coming out of those lenticulars was clean as a whistle. So in this case, the lenticulars were taking all of the load and generating a very clean wine onto the following membranes, which is what you want to happen. But if the colloidal material in that wine is sufficiently fine, it will go through the lenticulars and either hit the 0.65 or the 0.45, but they were lucky in this case. CMC is another one, relatively new additive, works fine, generally provided that the filterability of the base wine is good before the addition is made. In this case, it's sort of medium filterability, 9 and 12 for the indexes. But when the CMC was added, it jumped it up to 20 and 120, basically. Sometimes that will settle back down again, not always. And the general rule of thumb is that the higher the starting index is, the higher the likelihood is that you're going to have a problem once you add that extra colloidal material. And just lastly, one other thing you can do with filterability that many people aren't aware of is you can actually monitor your crossflows and just to make sure it's functioning as it should. In general, crossflows should spit out wine that has an index of certainly less than 5 and ideally around 1, 2 or 3 seconds for the primary index, something like that. We were running a filtration trial and got a call that there were some issues with the filters. So the first thing we did was check out the crossflow performance, very large crossflow in this case, lots of cells, 8 cells in this example. Collectively, once the outputs of those cells were recombined, it was still less than 1 NTU, so there were no alarms being triggered, but we knew there was a problem because subsequent filters were blocking earlier than expected. So I took the apparatus out and started measuring the cell outputs at different times. This is what you can see there. The cell identifiers are down the left-hand side, replicates, and then FI and modified filterability index. And you can see, for example, about half of those cells were showing significant problems. And throughout the course of running the filtration job, the filterability output was declining significantly and the filterability indexes were rising. So in the case of cell 1A, the outputs rose fairly quickly and the filterability of what was coming out of the crossflow was pretty terrible. If you look at those 3 replicates in terms of the flux curves and the appearance of the filterability test disc, you can see that there's some significant load that's actually sailing right through those cells in that case. And what is going on in some cases with crossflows, and this is why I said they're a good seller tool, but you do have to be mindful of the fact that they disrupt, or they can disrupt colloids. There are 2 types of colloids you find in wine, macromolecular and association colloids, and it's the second type that generally form issues in terms of filterability index elevation. Typically protein tannin complexes in reds, for example, that's probably the most common one that you're going to come across. And what we think happens is that in your wine, you have your protein tannin associative colloid. When you put it through the crossflow, you apply pressure across that 0.2, usually micron membrane, which tends to break up the colloids into their individual components. And over time, these will reform the association, not necessarily in the way that they were formed originally. And that time window can be anywhere from hours to days to weeks to months. And that reassociation of colloids may actually have a very high filterability index. And to give you an example of that, this was a Barossa Shiraz that was put through a crossflow. Half of the job was bottled immediately with no problems whatsoever. The filterability was perfectly fine. 2 months later, with no subsequent additions, they came back to bottle the other half, and it blocked the membrane very, very rapidly. And when we measured the filterability, it was terrible. It blocked the disc at about 300 mils, as you can see there. And the test disc is actually the bottom of that picture, and it's very red. Now, that's a polyether sulfone test disc. The fact that it's so heavily coloured tells you it's retaining a lot of colloidal material that is pigmented. And that's why I say it's most likely a protein tannin complex association. 0.55 NTU, so visually very, very clean, but from a filterability perspective, not so great. So that's the end of the presentation. Apologies for running through it so quickly, but there's a lot of material to get through there. And hopefully we'll have a few questions now, and if there are any subsequent questions further down the track, my email is there, or just find my phone number off the company website, and I'm more than happy to help anybody out.
Thanks, Paul. That was really interesting, and I really enjoyed that you gave a lot of examples or case studies from people and from some experiences that you've seen. So I think that really gives us a good idea of what's happening out there. There is a few questions that have come in. Jose has asked a question. How do you recover a crossflow that's being clogged up by filtering a wine that's had some CMC in it? And then they've apparently washed it with caustic, but I don't think there's any other treatments there.
Yeah, that's the problem with the example that I gave with the CMC is, yes, you if you have an issue, you will have some of the CMC will be retained, and you're never quite sure how much actually makes it through to provide the tartaric stability that you're looking for. You'd have to do a cold test there to check it on the filtered product. But how to get it off, gee, that's a tough one. If a standard chemical clean won't do it, I can't think of any enzymatic clean that would necessarily do it. Often get the same question with glucans after wet harvest wines and philibotrytis and so on, and that can be removed through an enzymatic clean, because a standard chemical CIP will not remove glucans. But I don't know of an enzyme that would necessarily chew up a CMC, so I'm not quite sure about that one. I might have to do a bit of research there and try and find out.
All right. There's a question on doing the filterability tests. Should they be done at just 20 degrees in the lab, or at the temperature that you're bottling at?
Yeah, the standard is pretty much 20 degrees. That helps you to normalise the data that you're going to get from the analyses. But the reality is that if that wine is going to be filtered cold, for example, with sparkling wines and so on, then it should be checked cold. But temperature has a massive influence on filterability, and it's always that the index is inversely proportional to the temperature. So the colder it is, the higher the filterability index is going to be. We've seen this many, many times over. So that's why we tend to standardise measurements at 20 degrees, and that might mean that you put your sample in a 20-degree water bath for a few hours, or 24 hours maybe, if you've got time before the measurement. But if the wine is going to be filtered cold online, then it should be checked relative to the temperature it's going to be packaged at. So you would chill that sample as best you can and then run it, and that will give you a much better idea of what's going to happen at packaging.
Yeah, that makes sense. We've had another question. How does potassium bicarbonate and COT affect filterability?
CO2, I guess, is it?
Possibly, yes. Yes, maybe spirit. Yeah.
Well, potassium bicarbonate's just a salt, so there's no major impact from that on the membrane per se. And really, CO2, I don't think there would be any significant effect from that either.
There's an update saying the CO2 is cream of tartar.
Oh, cream of tartar, yeah, okay. So are we talking about particulate material then, for example? So I guess that's what we're talking about, because again, with your filterability index, you're taking a raw wine and you're punching it through a final membrane test disc. Anything that's chunky, like tartrate crystals, is not going to cause any problem for that test, because it's just going to sit on the surface of the membrane. It's not actually going to bed itself into the membrane and cause you any great problems. And I think that example I showed in the correlation chart, where there was the top left-hand corner one had an NTU of 1.5 and an index of 0. That means the filterability is perfect, but the reflectance is high, and that tends to be what you get from things like tartrate microcrystals. So they don't usually cause a problem with a filterability test. It tends to be much more commonly colloidal materials that cause those problems. And bicarbonate, again, if it's dissolved and it's ionic, it really shouldn't cause any significant problem. Hopefully I've addressed the query there.
I think so. I had a question. I was just thinking of, like, we've seen a lot of uptake of Crossflows just in general, particularly in the cellar, for cleaning up wine and so forth. So I was just going to get you, well, we've got your opinion or thoughts on what you've seen in terms of changes in filtration, I suppose, of what's happening at the moment in the sector.
Generally, I think Crossflows are a fantastic tool. I don't really think they're ideal as a bottling tool for reasons that you've seen during the presentation, but they're very good at basically removing a lot of the particulate material that you don't want in your final product. But you have to bear in mind that they can cause colloidal problems, and we've seen it on many occasions. Probably the worst example I've seen is when a wine was had to be packaged and there were a heap of additions made to it just prior. I'm talking the morning of. Gum arabic was added, sulfur, which is no problem, some tannin, I think, also it was a real witch's brew. And then they put it through a Crossflow, tried to sort of clean it up and tried to package it. And when we measured filterability of what was coming out of the Crossflow for that one particular wine with all these additives, it changed every hour and it was getting worse, not better. So that's why I say Crossflows, I think, are a fantastic tool, but they do have the capacity to cause some colloidal effects in terms of wine filterability and stability. And you just have to be aware of that, keep it in mind. And I think a general rule of thumb is if there are no immediate additions, if you've got a wine that's relatively stable and you want to put it through a Crossflow and then package it, that's likely to be fine. Generally, the earlier or the narrower the window between exiting Crossflow and getting into the filtration skid, the better it's going to be. But if you give that thing time to reform some weird colloidal associations, then that's when you can start to see problems.
I suppose that's your messaging as well with filterability index. If you're doing that test, you're doing it on the finished wine product in the packaging tank. Not prior to those last minute additions or tweaks and so.
Well, yes, that's right. And I've seen examples where winemakers have wanted to add certain things to a wine. They've gone into a facility that has a filterability apparatus and they've said, I want to add this tannin or whatever it happens to be. You can actually do it on the bench immediately and then run it through the filterability apparatus and see what it's going to do. And 9 times out of 10, when they see how bad the impact can be, they won't actually add it. Yeah. So we've had examples of that taking place as well. And that's just staved off a packaging problem because nobody wants blocked filters. Nobody wants the process to stop because that's detrimental for the packager and potentially for the wine as well. So it's all about empowering both sides of the equation of the relationship and streamlining the process as much as possible.
Yeah. We've got another question, which does relate similar to the very first question you answered, looking at treatment for cleaning up Crossflows if it's blocked by bentonite, PVPP, glucans. I think you mentioned glucans earlier. Yeah, but I suppose if bentonite, PVPP.
Well, they're real problems. I think for some types of membrane within a Crossflow more than others. Generally, we actually advise to keep those sorts of products well away from a Crossflow. And a simple way to do that, one of the filter types I mentioned in the beginning was a bag. And I didn't talk about it specifically, but bags are very inefficient filters. They don't filter terrifically effectively, but they're very good at catching chunky materials like earth and PVPP. So I always recommend that you actually run through a bag filter on the way to the Crossflow just to keep those sorts of things out, because once they're in, they can be